This is the solution to Chapter 13, Video Assignment 2. The question states, recent catalytic converters, in addition to reducing emissions of carbon monoxide and unoxidized hydrocarbons, reduce nitrogen oxide pollution. In a chamber filled with air, and instructions to look up the partial pressures of nitrogen and oxygen in dry air. At 2100 degrees Celsius, the reaction that generates nitrogen monoxide from nitrogen gas and oxygen gas has an equilibrium constant of 0.050. What are the equilibrium partial pressures of the three gases in the above reaction after the reaction? And remember, vehicles don't run in alveoli, so yeah, we're not in the lungs, so not important. So first off, we're instructed, it gives us the question that it's nitrogen gas and oxygen gas, which we know is N2 and O2, react to form nitrogen monoxide. So I just wrote a balanced equation. All right, these are present in the atmosphere in this form, so we're going to have two nitrogen monoxide on the other side of the equation to balance it out. I googled composition of dry air, 78% nitrogen, 78% oxygen. So Dalton's law of partial pressure states that if it's 78% times 1 atmosphere, we're going to have 0.78 atmospheres of nitrogen gas and 0.21 atmospheres of oxygen gas. Now, given the balanced equation here, we can write an equilibrium constant expression. So Kp is equal to the concentration of nitrogen monoxide squared, here, right? Divided by the product of the concentration of nitrogen gas and the concentration of oxygen gas. So we're given that is 0.50, the question. Now, using these values, we can construct an ICE table or ICE table. So for our initial values, as aforementioned, we got 0.78 here, 0.21, and we'll assume that nitrogen monoxide is starting there at a concentration of 0. So the change, obviously we're going to look at the stoichiometric coefficients here. These are going to react, so we'll have minus x for the 1, minus x for the 1, and then they're going to form twice as many 2 nitrogen monoxides. So the stoichiometric coefficient here is going to have us have 2x. So minus x plus 2x. So using some algebra over here, we can say 0.050 is equal to 2x squared. I just left the 0 out for obvious reasons. So 2x squared divided by 0.78 minus x times 0.21 minus x. Now that equals to 4x squared, timesing across, 0.1638 minus 0.7x minus 0.21x plus x squared. And times this by here, multiply this by this side, 0.00819 minus 0.039x minus 0.0105x plus 0.05x squared equals 4x squared. Now we'll subtract off the 4x squared from, this, and also we can sum these. So that leaves us with negative 3.95x squared minus negative 3.95x squared from this, negative 0.0495x from this, plus our constant of 0.00819, or that number, constant, yeah, okay. Anyways, all equal to 0. So put that into a quadratic solver. X equals two options, obviously. One is a negative number, so we can just toss that out immediately. It's not physically possible. And the other is 0.0397. So, going back to our ICE table, we can subtract 0.78 minus 0.0397, leaving us with 0.74. The same here gives us 0.17, and 2 times 0.397 is equal to 0.079. So, in this reaction at equilibrium at 2200 degrees Celsius, we have a concentration of nitrogen gas of 0.74 atmospheres, or partial pressure. I was saying concentration, but that's kind of analogous with partial pressure for this example. So partial pressure of nitrogen gas of 0.74 atmospheres, partial pressure of oxygen of 0.17 atmospheres, and a partial pressure of nitrogen monoxide of 0.079 also atmospheres.